Welcome to Matematika. Today we're going to do 1.10 rational functions and wholes. A whole or removable point of discontinuity in a rational functions graph occurs when there is a real zero in the numerator and denominator that divides out, especially if the multiplicity of a real zero in the numerator is greater than, or equal to its multiplicity in the denominator. What's the difference when we're looking to the vertical asymptote? We're trying to find out which multiplicity is greater than, and if the multiplicity of the denominator is greater than the multiplicity in the numerator, then there is a vertical asymptote. Well, in a whole here, the numerator is greater than the or equal to the multiplicity of the denominator. If that happens, then there is multiplicity of real zero in the rational function. If the input values to the left, okay, let's say in the graph, this graph right here. All right. Let's look at the graph. In the graph of rational function, let's say we call this function as r of x, has a whole at x equals c. So let's say this is c right there, point C. We know what is c in this graph, but in case that stands for c, then the location of the whole can be examined by examining the input and output pairs close to the C. That means we are trying to get the coordinate that is close to that C where the whole is located. If the input values just to the left and right of C correspond to the output values very close to a specific number L, okay? Let's say we call this L, that specific number. The whole is located at the point where the coordinates. This is located where the point of the coordinates is C and L. Okay, that is the meaning of that. So in this case, we're going to deal this afterwards. So the function r of x, let's say the function, let's have a function r of x. We have x plus 1 times x plus 4 over 2 times x plus 1 times x minus 2. That is the one that corresponds to in the graph. Okay. The graph has a whole at x. Okay, the whole is located here at x equals 1, negative 1. That's the location of the whole. All right. Because the fact, okay, let's look at our function here. We have the factor that we can see in the numerator and can be seen in the denominator, which is the x plus 1 that appears both in the numerator and denominator. So we cancel that out. Once we know that, then we know what's the value of our whole. Coming from x plus 1 equals 0, then x is negative 1. Without looking at the graph, if you are just given the function, then you will know right away the location of the whole. So By examining the limits as x approaches -1, we are now trying to get the value of L in order to find the location of the hole, for example, if the graph is not given. So by examining the limits as x approaches -1, from the left or from the right, the left of C and the right of C, or from the left of x equals 1 or from the right of x equals 1. So we're going to start from the left. Okay? So if this is, let's say if this is the location of -1 and this is -2 right here. This is the left of -1. So what probable numbers that we can have closer to -1? Maybe we can have -1.01. We can have 1.25 or -1.1. Okay, so we're gonna try like R, let's say very close, closer, -1.25. Replacing that to the function. Okay, so if you have 1.25 plus 1 times 1.25, that's negative, plus 4, then 2 times -1.25 plus 1 times -1.25 minus 2. Okay, by doing all the math, by computing, we come up with a -0.423. Okay, doing the same thing, let's choose 3 numbers, which is very close to -1. Let's say a -1.1. Okay, substitute to the function and we come out with a -0.468. Let's say if we substitute a negative, closer, very close this time, still you come up with a -0.497. So what have you observed? 0.423, 0.468, 0.497. So the more it is close to -1, the value of y approach to approximately 0.5, right? Closer to 0.5. So let's do the same thing from the right. So from the right of -1, this is our -1, this is 0, right? So that means, what are these numbers that can be used in order to find out our L or the y value for the coordinate? So let's choose like, okay, let's say 0.75. That's close to -1 from right. We come up with a -0.591. When R let's say 0.9, this time it's very close. And then the result is 0.534. Doing all the substitution to the function, I'm not just showing it, but it can be computed, and this is the result. If I replace a very, very, very close this time to -1 from right, we come out with a negative 0.503. Okay. We can see here still it is, we can see from its direction, from left or from right, as x value gets extremely close to -1, very close to -1, the y value approaches to -0.5, or the limit notation. All right. So we could write that here, the limit notation as x approaches c, this will be the formation of the limit notation. The r of x up is equals to a 0.5. Okay. So whether the limit is from left as x approaches c from left, the r of x is -0.5. The limit as x approaches c from right, the r of x is -0.5. That is what's going to happen if you are asked to find the coordinates of the location of the hole. Now, in this case, if we are just looking at the graph, we could tell right away where the location is. Look at this. The location is -0.5. Okay? As this x approaches to the hole, it is at 0.5. From the right, as it approached to the hole, it is at -0.5. Okay. It's easy to look for the coordinates if you have the graph. Then if you don't have, do this process by computing and putting an input numbers that are very close to the location or the x value of the hole to get the y value. Okay. So the location of the hole in a rational function can be determined by examining the limit function as it approaches the input value of the hole. Let's have an example here. All right, let's do this. Consider the rational function f of x equals x squared minus 2x squared, x cubed minus 2x squared minus x plus 2 over x squared minus 1. Identify the x values for which the f of x has holes. So you have to examine first. Look at the function that are given. So the function here has 4 terms. Okay. So in other words, we have to factor the numerator, and this is x squared minus 1. Factor the numerator and also as well as the denominator. So by looking at our numerator, we have x to the third power, and we have 4 terms. So the only easy way to factor this out by doing by grouping, right? So if let's say Okay, I'm going to do this. The numerator, you can factor out by grouping x cubed minus 2x squared. And you group as well the x plus 2. You can do that grouping over there. So by doing this, the common in the first factor is x squared. So you have x minus 2. So the other one is x plus 2. You have to look for a common factor. That's why you can put a negative 1 out by multiplying negative 1. Then this will be x minus 2. All right. Okay, I have to rewrite this. So we can find a common factor this time. We have now x squared minus 1 and then the common factor. All right. That is the numerator. Now in the denominator, that's the difference of 2 square. So our denominator would become like x plus 1 and x minus 1. Right? Or I don't need to do this stuff right here because I could see that it's x squared minus 1 and the denominator is x squared minus 1. So might as well I could have cancel this out, or I could show. Let's do this. The numerator x squared minus 1 is x plus 1 as well, and x minus 1, then x minus 2, and then our denominator is x plus 1 and x minus 1. Okay. So we can see now that there are two common factors between the numerator and the denominator, and they are x minus 1 and x plus 1. Okay, so this means if I cancel this out, there are holes at x equals 1 and x equals negative 1. Because x plus 1 equals 0, x is equals to negative 1. And the other one is x minus 1 equals 0, then x is equals to a negative 1. All right. Oh, I have a big space here. All right. Anyway, identify the coordinates of any holes. That means this time we are going to look for the y value. There is no graph, so it's not that easy. So one hole is located at x equals 1. All right. So let's say, what are the numbers that are closest to 1? I will just choose 2 to go directly, like x equals, this is very, very close. I use 3 digits. And x equals, let's say 1.001, 3 digits as well. All right. So let's do this. What will be the function if it's 0.999 and replace it to the equation? X minus 1, replace the x value. 0.999 plus 1, and then 0.999 9 minus 2 divided by 0.999 minus 1 and 0.999 plus 1. Okay, doing the math, you come up with a negative 1.001. Do the same thing if you use a 1.001. Do the same thing by doing that. Okay? 1.001 plus 1.001 minus 2. Then you have 1.001 minus 1, then 1. But actually, if you have a calculator, having small number like this, you can do this in the calculator. But in case you are not allowed to use a calculator, you can do this process. Just choose any number that is very, very close to the left or from the right. Okay? So these values 0.1001 and negative 0.99, these values right here, these output values are getting extremely close to negative 1 as we approach the hole from the side. So the coordinates of one hole can be, we just approximate that, one coordinates can be when x value is 1, the y value is negative 1. These are closer to approximately negative 1. Negative 1. Do the same thing. Located at negative, the other hole is located, what's the other hole? Negative 1. When x is at negative 1. So do the same thing. Let's say we choose the value of x. Let's say I choose the value of x as negative 1.001. X, I do the same thing, 0.99. This time it's negative because it's our value of x is negative. So replace that to the function of negative 1.001. Do the same thing by doing this. Minus 1, negative 1.001 plus 1. Replace that to the function, minus 2. And then we have 1.001 minus 1, 001 plus 1. By doing the math, we come up with negative 3.001. By doing the other one, this time it's very, very, very close. Okay, to negative 1. So you have 0.999 minus 1. Replace that to the function. 999 plus 1. 0.999 minus 2. And then you have a negative 0.999 minus 1. And negative 0.999 plus 1. You come up with a negative 2.999. Actually, if by doing this, you can actually cross that out. right? So when you have two negative 999 and then add it with a negative 2, then you come up with a negative 299. And doing the same thing with this, you can crush that out. So by just looking at it, then you can crush this out. All right. So by these output values are getting extremely close to negative 3, right? Negative 2.99 very close to negative 3, and negative 3.001 is close to negative 3 as we approach the hole from its side. So the coordinates, we can have a negative 1 and negative 3. This is the coordinates of the other hole. Okay, we found this coordinates. Okay. Right. So I think you don't need a calculator by doing this. I was just looking at it. Okay, you can have that. You crush that out and then you cancel out. I'm just showing how you're gonna find the y value or the output value. Example 2. Consider the limit notation for a rational function. I think the rational function was not written here. Let's say the limit as x approach 3, the function of x is equal to 4. So first of all, by looking that, you can interpret the location of a hole on the functions graph based on the information here. So this notation, we could say that it means, if we look at the meaning, that as the means that as the input value values approach 3, what is the output value? The output values approach 4. I think that is how you do the reading there. So the hole is located at 3 in x and 4 in y. Input is 3, output is 4. Okay, I think that's it. Let's have number 3. Find the hole or holes, if many, of the following rational function. Okay, let's do this. F of x is equals to x squared minus 36. Okay, so if we factor out, I'll write it here. If I factor out the numerator, this is difference of two squares. So this will be x plus 6 and x minus 6, right? And as well, in our denominator, you have x squared minus 8x plus 12. So the factor of 12 is 2 and 6. And our middle term has a negative. That means it will be x minus 2 and x minus 6, right? You have two negatives there because your middle term is a negative. Negative 2x and negative 6x is negative 8x. So we can see that there is a whole at x equals 6. You're just asked to find the whole. No more, no less. So in this case right here, g of x is 5x squared plus 20x over x squared plus 9x plus 20. So we have to factor out what's common. Common is 5x, right? Then we have x plus 4. Factor out the common term between 5x squared and 20x squared. Okay? In our denominator 20, we factor out 20 by 4 and 5. All positive. So no problem. You have all positive for factoring. Alright, we can see a common factor in numerator and denominator. That means the whole is located at negative 4. Coming from x plus 4 equals 0, then x is negative 4. Okay? For number 2, we have t squared plus 12t plus 36. Okay, factor. What's the factor of 36 in such a way that you add 9 and 6 and 6. Okay, 6 and 6. T plus 6, t plus 6. All positive. Okay, in the denominator, 30, t plus 6 and t minus 5. Since our last term is negative, so our factor should be that way. So we have a whole there coming from t plus 6. So t is negative 6. That's where the whole is located. Okay. I have so much space here. Let's have the fourth one. Now this time, use the graph if function to find the wholes. Use the limit notation. So the first thing you have to look at is where is the location? Where is the x value in the whole? This one in this, I will blow this up. The whole is located at positive when x is equals to 1. Right here. Okay. Now, I will write the limit notation. So the limit as x approaches 1 from left, what is the function of x equals to? What's the output? The limit as x approaches 1 from right, what is the function of x? Okay, so this is the left side and this is the right side of 1. So all you have to do is from your graph right here, as it approaches to the whole, the output value is negative 2, right? Approach closer to the whole, it's at negative 2. As from the right side, as the numbers approach to the whole, or what number you're going to use here, closer to 1, it approaches to negative 2. That means our y value is negative. Output value is negative 2. Okay. It's just looking at the graph. Let's have the B. right here. Where is the location of 1, 2, 3? Right here. X is 3. That's the location of our hole. So you could say that the limit as x approaches 3, right, from left, the function is what? As limit of x approaches 3 from right. Sorry. Function of x is what? So this is the right, this is the left. Give me a moment. As x approaches closer, it is at 1, 2, 3, 4, 5. Right here. 5. Same thing with the right. As it gets closer, it approaches to 5. That means the function of x here is 5. Okay. I think it's common sense. The way you see it, just cross and find the x and y value from the graph. Okay, I go directly. So where is our location here? At x equals -2. So we can write down the limit as x approaches -2 from left. Limit as x approaches -2 from right. So the function of x is at where? At -2, right? Because by common sense, this is the left, this is the right. If we try to get these values right here, it goes very close to -2. Same thing from the right, very close to -2. Right there. Okay, that's it. Now, I hope everything is clear when it comes to holes in the rational function. We'll do more about holes in the problems and solutions in my next video. So all I can say is that if I can do it, so can you. Please don't forget to hit the like button and the subscribe button. See you in my next video.